Say you have a lecture hall worth of students taking a multiple choice exam, and instead of studying over the past few weeks, they all decide to answer every question randomly. If everyone played along, the scores would look like this. Most would score right around 50, while some, by pure chance, would score very high or very low. If you let the lucky ones take the exam again using their random guessing shenanigans, they wouldn't all hit home runs again. Their scores would actually look like miniature versions of the entire class. While some would score high again, some would score low, but most would float back down around 50. Likewise, the same thing would happen with the students you wouldn't want to take to Vegas. They all wouldn't just bomb again. While some would score low again, some would score high, but most would rise up to right around 50. You might be thinking that no one would guess randomly on every question, and you're probably right. If students didn't choose randomly at all, then every student would be expected to score the same on the second round as they scored in the first round, and this weird side effect would just be dust in the wind. But if there's room for any chance whatsoever, this side effect tends to show up. It's commonly known as regression to the mean, and it was first documented by Sir Francis Galton in his 1886 paper. All the while, being busy founding psychometrics, devising methods for classifying fingerprints, creating the first weather map, pioneering the use of questionnaires, conceiving of a measure to quantify normal variation, also known as the standard deviation, and inventing regression. Safe to say, the dude was busy. He noticed this when looking at how tall kids were. He examined the heights of 930 kids and compared them to their parents' heights. He found that the kids were actually closer to the average height than their parents were. That is, tall parents actually tended to have kids who were closer to the average height, even though some did have tall kids. And that short parents also tended to have kids closer to the average height, even though some did have short kids. This flew right in the face of common perception and intuition. Heights aren't completely deterministic. Most realistic situations fall between the two extremes of 100% random and 0% random, sort of like a balancing act. Remember the exams and the students? You could think about them as a combination of skill and luck. The students who scored high in round 1 were probably either skilled and had no especially bad luck, or were unskilled but got extremely lucky. When round 2 comes, it's the luck that's being re-rolled like a die, not the skill. The unskilled probably won't catch another lucky break, while the skilled, although prepared, will have a second chance to have bad luck. This is the regression to the mean bit. Those who did well previously are unlikely to repeat their success, just like the tall parents, who are actually more likely to have average height kids than more tall kids. And it's a similar story for the students who scored low on round 1. They're likely to do better in the second round just by pure chance, just like the short parents, who are more likely to have average height kids than more short kids. The idea of more skill leaves less up to chance might seem really obvious, but it's seriously overlooked far too often. Suppose you are testing a new drug for a terrible disease. I can't think of any good recent examples in 2020, so you'll have to use your imagination. You take the worst of the worst in the population and test the drug with high hopes to find that, after the first treatment, their conditions have improved. Great news, right? Remember the students? If you can't rule out randomness completely, then part of being in the worst of the worst is due to bad luck, like students who did poor on round 1. They were either unskilled and just not lucky enough, or skilled and really unlucky. And the improvement could be just the right combination of skill and luck. In other words, patients would be expected to improve a certain amount just by random chance. But by how much? And how much is because of the drug, if any? This is where control groups come into play. Having a group from the same worst of the worst population who don't take the drug at all lets you see if the drug improves health more than random chance would by itself. Any change in the control group is regarded as change due to random chance, and the leftover change in the drug group is regarded as change due to the effect of the drug. So what's the big deal? This is exactly what led instructors to believe that negative feedback trumps positive feedback. Students who did poor and got negative feedback would tend to do a little better afterwards, while students who did well and got positive feedback would tend to do a little worse afterwards. Luckily, psychological trials with control groups have shown that this view is totally backwards, and that regression to the mean was likely the guilty culprit. But without a control group, it's easy to be fooled, since it's impossible to tell what caused what. A wise man once said, "If something varies normally between two far extremes, it usually swings back naturally to values in between." From sport to crime and illnesses, we see this common theme, an effect we call, statistically, regression to the mean. Evidence-based treatments that doctors should assign use tests that will be randomized, controlled, and double-blind. Stopping self-deception before test results are seen stops them from being fooled by regression to the mean. If you like this video or would like to hear about other topics, subscribe, hit the like button, leave a comment.